All right, so this is going to be section 2.8. It's actually the last section of Unit 2. And what we're doing here is we're going to be looking at modeling, solving application problems with our higher order polynomials. We're going to look at sort of two sections of them, two types. The first type are going to be the ones where the description of the problem is given or an equation is given, and we just have to use it. And then the last example we do today, we'll have a data table where we'll actually have to generate our own equation. All right? So in number 1 here, and by the way, I'm changing these instructions. Anytime you do modeling problems, application problems, either on homework or on tests, I'm not going to require you to work by hand. You are welcome to use technology on all of these. All right, so it says the top and bottom of a cardboard box are squares with sides of length x inches. The height of the box is 18 minus 2x. Write a function v of x that represents the volume of the box. So I'm going to sketch it here real quick, although it's not absolutely necessary. We have this box with a square base, and the square top and bottom has sides of length x. So x and x. The height is 18 minus 2x. And definitely the volume of any box is length times width times height. So to write my volume as a function of x, I'm just going to literally multiply length times width, x times x, times height, 18 minus 2x, which is x squared, times 18 minus 2x. I'm going to leave that in its factored form. If I want to multiply it out, if I need it multiplied out later on, I can always do that. But typically factored forms are helpful. So I'm going to go ahead and leave the factored form here. Okay. So there's my volume equation, just length times width times height. All right, this function is a polynomial. And we know, we've been seeing this for a while now, the domain for polynomials is always all real numbers. But in an application problem, sometimes not all real numbers actually make sense. I'm going to say, what is the effective domain in order for this box to be realistic? Well, hopefully you'll agree with me that in order for the box to be realistic, I have to have positive numbers for the length, width, and height. I can't have a negative dimension to my box. So for sure, x has to be greater than 0. That takes care of the length and width being positive. But also, 18 minus 2x has to be positive as well. My height has to be positive. So that would say 18 is greater than 2x. And if I divide by 2, 9 is greater than x. I could read that as x less than 9 if I want to. So it looks like my x values are between 0 and 9. Can't be negative and can't go any bigger than 9. So my domain is from 0 to 9. Does that seem logical? Good enough. All right. So the next thing I'm being asked to do is to find the dimensions and the volume if my square top has sides of length 7 inches. So what I'm basically being told here is the square is 7 by 7, right? Or in other words, x equals 7. And first of all, the dimensions, the 7s are the length and width. Make this a little bit bigger so you can see more. But I also need the height to give all the dimensions. So then I'm going to say my height would be 18 minus 2 times 7. 18 minus 14 would be 4. So my box is 7 inches by 7 inches by 4 inches. Dimensions, just length, width, and height listed out. To find the volume of the box, I have a couple of choices. Since I actually know the length, width, and height, it would be perfectly fine just to multiply those together. 7 times 7 times 4. $196. And that would be in cubic inches. Or, just to test our volume function, we could have also chosen to say, well, since x is 7, I could just put 7 into that volume function. That would have given me 7 squared times 18 minus 2 times 7. Notice you can see length times width right here, times height there. And of course I'm expecting to get the 196 again, but let's just verify that. If I take 7 squared times 18 minus 2 times 7, of course I do get that 196 again. So once you know the dimensions, you can just multiply them together, or you can use your volume formula that you already developed. You'll get the same answer either way. All right, question D says, what dimensions of the box will give us a volume of 160 cubic inches? And again, I said I'm not going to ask you to do them algebraically. We're just going to do the problem graphically. All right, so I know the volume is 160. I'm going to go back to my volume equation, and I'm going to put 160 in on the left-hand side for the volume. So I have 160 equals x squared times 18 minus 2x. Now again, there's multiple ways to solve that, even graphically. But I'm going to go ahead and do this kind of using the technique that we have most often used, which was when we want to solve a polynomial equation. We said in section 2.6, we can get it equal to 0, and then just look for the x-intercepts, right? So I could say 160 equals 18x squared minus 2x cubed. And I'm going to bring this over so I'd have a positive 2x cubed, a negative 18x squared, plus 160, and that's now equal to 0. Since I've got it equal to 0, I'm just going to graph it and use the x-intercepts. Make sense as a strategy? All right, let me get Desmos going here. And if I get rid of some of this old stuff and enlarge my graphing window again. All right, I'm going to go ahead and I'm going to type in the function 2x cubed minus 18x squared plus 160. And it's huge, so I'm going to adjust my axes here a bit. There we go. There's a little bit better window that I can actually see. All right, you can see that there are actually 3 x-intercepts. So let's go ahead and identify those first of all. According to Desmos, and I'm jotting these down on my paper right now, I get x equals about negative 2.62, or x equals 4, or x equals 7.62. Right? So I just wrote those down, and I'm going to come back and we'll talk about them. All right, so there, according to Desmos, are the 3 solutions to this equation. I'm sure you'll all agree with me that I can throw out the negative 1 right away. I can't have a negative dimension to my box. So this one's not realistic. X equals 4 works though. Remember, that's both the length and the width. But we could figure out the height that goes with it. 18 minus 2x, 18 minus 2 times 4 would give me a height of 10. So let's see, this one would be 4 inches by 4 inches by 10 inches. That would be one possible answer. That would be a box that has 160 cubic inches as its volume. And this one actually works too. Notice it's between 0 and 9, so it's going to work. Again, this is the length and width. So my height, 18 minus 2 times 7.62, just doing that on a calculator. Is 2.76. So this one, length and width are 7.62. And the height is 2.76. Okay. So there were 2 possible ways to get a box of this shape to have that volume of 160 cubic inches. Questions at all about that? Throughout the unrealistic one, and then followed through to calculate that 3rd dimension, the height, on the 2 that were realistic. All right, last question on this one. What dimensions of the box give the maximum possible volume? And it specifically says to use a graph, but we're using the graph for all of these. So when I think maximum possible volume here, I'm just going to look for the max on the graph. So let me go back over to Desmos briefly, and we'll just find that max, then we'll talk about what it's telling us. All right, there's my graph again. And you can see that the maximum actually occurs right there. Now, I don't think that one's very realistic. Hang on. Did I mess something up here? Let me just make sure I didn't do something wrong, because it's not quite what I was expecting. think I've got everything okay. All right, so you know what? It's all right. We're going to go ahead and we're going to say, oh, I know what happened. I didn't graph the volume equation. My fault. I knew there was something weird here. Let me go back over here. I graphed this function because I had wanted to solve that equation, right, where the 2x cubed minus 18x squared plus 160 was equal to 0. But that actually isn't my volume equation. Let me go back here and actually graph my volume equation. In fact, I can even call it v of x, the volume. And my volume equation all the way back to part A was x squared multiplied by 18 minus 2x. There we go. That's more right. Good. All right, so that's my actual volume equation. And so it's the max on the graph of v of x. And here we go. It's right over here. 6, 216. Now that I got my head in the game, everybody okay with that? All right, so what's that telling me? Well, I know the x value here is the length and the width. The y value is the actual volume, since I graphed v of x. So if my goal was to find the dimensions, I know the length and width are both 6. I know to find the height, I take 18 minus 2 times that 6. 18 minus 12 would also be 6. So I'm going to end up with a perfect cube, 6 by 6 by 6. Gives me the maximum volume. And that volume is 216 cubic inches. Right. Everybody doing okay with that one? All right. We have one more kind of descriptive problem, and then we'll do the data one. So in number 2, the profit P in millions of dollars made by a t-shirt manufacturer is given by this equation P of T, where T is the number of t-shirts produced in millions annually. Okay. So this time we don't have to come up with our own equation. They actually gave it to me. Right. I want to find the P-intercept and explain what that means. And then I want to answer the question, for what values of T does the manufacturer make a profit? And then I want to figure out where the largest profit would be. I'm going to answer all of those questions from Desmos. So I'm actually going to go ahead and just stay on Desmos for this whole problem. And I'm going to start by graphing my given function, P of T. And it is negative T cubed plus 4T squared plus T minus 4. And I probably have a little bit bigger y-axis than I really need. There we go. That's not bad. All right. So first part is, what is the P-intercept? And explain what that means. Remember what your intercepts are, right? For any intercept, you set the opposite variable equal to 0. So to find the P-intercept, I'm going to set t equal to 0. I can see that on the graph. When t is 0, I'd have my P-intercept right there. Or I can also just do P of 0 from my function notation if I want to. And I get -4 that way as well. So P of 0 is -4. And since this is a profit equation, that actually would mean a loss, right? A negative profit would mean a loss. Well, that makes sense. T is 0. I'm selling 0 t-shirts. I'm going to have a loss just because I'm going to already have invested in my building and my equipment and paying my people and all that stuff. If I sell no t-shirts, I'm going to lose $4 million. So that's part A. All right. Part B asks us, for what values of t does the manufacturer actually make a profit? Well, if we're going to make a profit, that means that the profit P would be positive. So notice, from here to here, right? Profit is positive in here from t equal 1 to t equals 4. So what that means is that, and that was actually the answer to the question. I guess I just said for what values of t, but I could explain just a little bit more. If I make and sell between 1 and 4 million t-shirts, we'll make a profit. All right, part C says, for what value of t do we get the largest profit? And you can see over here we'd have a maximum right there. So it looks like to get the largest profit, we would have a t value of 2.7, I'm going to round that to 2.8, and a p-value of 8.2. So I'm just going to write that down. The max is at 2.8, 8.2. And again, that just came from rounding those values. The input is t, so we're making 2.8 million t-shirts to achieve a maximum profit of $8.2 million. So just all the stuff I can just really read off the graph there. Questions at all about that? All right, my last one, instead of giving us a description or actually telling us the equations, the last one shows us the cost for manufacturing some cars. So let's go back and take a look at that one. This table shows the cost C in thousands of dollars to manufacture X Chevy Cobalts. Right? So just kind of taking a little bit of a look at here, if we make no cars, it's going to cost us $10,000. That's probably just the overhead, you know, keeping the lights on and that kind of thing. If we make one car, it's costing $23,000, all the way up to if we make 10 cars, it costs $135,000. It says we're going to use the calculator to draw a scatter plot. In other words, plot the points, and then identify the type of function that best fits this data. I want to talk to you a little bit about type of function for these higher order polynomials. I'm going to move away from this for just a second and talk in general. Think back for just a minute to section 2.5, and I want you to particularly focus on the difference between even degree and odd degree polynomials. If your polynomial had an even degree, we knew that the end behavior would be like the parabola, either both ends up or possibly both ends down if it was reflected, right? But both ends go in the same direction. Now, other things might happen in the middle, right? Sometimes you got other weird things going on. But as long as the two ends go in the same direction, we can assume that this is going to be an even degree polynomial. Odd degree polynomials, our end behavior was like those wave functions. So like that, or possibly if it was reflected, like this. But either way, the ends go in the opposite directions. One goes up and one goes down. Once again, you can have other stuff happening in the middle, right? I could have maximums and minimums happening in the middle, and that would be fine. But as long as my ends go in opposite directions, I'm thinking this is going to be an odd degree polynomial. This is the criteria that I'm going to use to decide whether to choose an even degree model or an odd degree model when I look at the points that we're going to plot here in just a minute. Okay? For the purposes of this class, when you're modeling, when you're doing your data tables and trying to come up with a model, we will never have anything bigger than fourth degree and third degree. So if it's even degree, we're going to use n equals 4 or a fourth degree polynomial. And if it's odd degree, we're going to use n equal 3 or a third degree polynomial. The actual fact is, in the real world, higher degree polynomials just don't arise that often. So using third and fourth degree ones is going to be plenty for us. Okay. So let's just review real quick what those look like. An even degree with n equal 4. You're going to tell Desmos, I want a fourth degree polynomial. y1 with that tilde. And that would be ax1 to the fourth plus bx1 to the third plus cx1 squared plus dx1, right? We're just doing all the powers from 4 on down, plus a constant term, which I'm going to call f. We do want to avoid using e here. You may have remembered from another class, e is a special number in math, right? It's Euler's constant. We're going to be talking about it more in the next unit, but e means something special in math, so don't use e as a variable. Use f instead. If we have an odd degree, so we end up wanting to use an n of 3, then we would use y1 is ax1 to the third plus bx1 squared plus cx1 plus d. Right? Whatever your highest power is, you just have a term for all of the powers on down to the constant. Right? So those are the two possibilities that we'll be looking for when we do our data table problems here in section 2.8. All right, let's see which one we actually have. So back to my car data here. I'm going to go over to Desmos, and I'm going to put this data in. We'll decide which kind of equation we want, and then we'll actually do the regression to find our function. Okay? So let me get that far first. All right, so let's see. Get rid of all this. And I'm going to put my table in here. I'll put all of the car numbers, so from 0 to 10 in my x's. And then bear with me for just a minute while I put the costs. All right, I'm going to use this little zoom fit to see what's going on. All right, so you can see the scatter plot, and I'll point out it's not really quite linear. You can, I mean, you know, you could do an equation of a line, but it wouldn't be a great fit. You can just definitely see some curve in here. Right? My ends seem to be going in opposite directions, right? Down over here on the left to up on the right. So since my end behavior is in opposite directions, I'm thinking I probably want to use an odd degree polynomial. And as I said, for our purposes, we'll never go bigger than 3. So I'm going to say end behavior in opposite directions. So use an odd degree. In our case, we'll use a cubic, or n equal 3. And again, that's a limitation I'm putting on for this class. Any odds will use 3. I mean, it could be 5, 7, 9, whatever, but I'll never ask you one where you need more than an n of 3. All right, so then we're supposed to, that's part A. In part B, we're actually supposed to do the regression. So I'm going to say y1, and then I use that little tilde to tell Desmos, hey, I want you to find me an equation now. And for third degree, it would be a x1 to the third plus b x1 squared plus c x1 plus d. And we can see a couple of things, right? We can see a really, really good fit. I mean, boy, it looks like it comes super close to all of those points. And my r squared value over here is 0.9997, so very close to 1, telling me I've got a very good fit here. And then it gives me the value of a, b, and c. I'm going to write these down on my paper in case we come back to it, but then I'm also going to type this in as a function in Desmos. So my function c of x, if I round to say 3 decimal places, would be 0.126, excuse me, 0.216. And that would be x to the third, minus 2.347. That's my b. And that would be for x squared. My c, plus 14.328. That would be x, plus 10.224. For D. All right. I've got the graph here and it's already in, but I'm going to go ahead and type in my own function. So this is really the answer the way you'd want to see it for part B. C of x, which is the name they told me to give it, all right, and you can see that that kind of purplish graph that I just drew went right over the green one, so it's the same graph. I just wrote it in function notation now. All right, I'm going to turn off their green one, and I'm going to turn off these points so they don't distract me as I answer the rest of the questions. All right, so there's my model. The next part, part C, wants the cost of manufacturing 11 cobalts. Well, the number of cars is actually just my x value, so I can find that pretty easily just by plugging x here, plugging in 11. So C of 11 is 171.34. This is in thousands of dollars. So I could say cost is $171.341 thousand. All right, part D. We wanted to find and interpret the C-intercept. So remember, any intercept, you always put 0 in for the other variable. So I'm going to put x equals 0. And if I do that, I can just say C of 0 is 10.224. So this would say if I make 0 cars, my cost, and this you could think of this as the overhead, my cost is a little over $10,000. Right. Question E says how many cobalts could be manufactured for $300,000? All right, first of all, be a little bit careful with this question. I've given you the actual amount of money, but remember in the table, the cost was in thousands of dollars. So what I'm really saying here is the cost is 300 thousands of dollars. One kind of nice way to answer that would be to just go ahead and use the graph I already have. And if I add the line y equals 300 to my graph. My graph wasn't quite big enough to show it. I only am seeing up to about 200 right now. But if I change my perspective so I can see all the way up to the 300, there we go. There's that y equal 300 line that I just added. And you can see that it's about 13.39 here that gives me a y or c value of 300. So I'm going to say it's x equals about 13.39. Now x is a number of cars, and I've made 13 whole cars. I don't quite have enough to make the 14th, so we can make 13 cars. All right, that actually brings us to the end of section 2.8 as well as the end of unit 2. So I'm going to encourage you to not only, of course, do the homework for this section, but this is the time you want to start working on the review sheet as well for unit 2. The midterm will cover both units 1 and 2, so you're going to want to review back in unit 1 as well as unit 2. And definitely kind of watch for an email as well. I'll be emailing some more information about the midterm to you very shortly.